In previous lessons, we have focused on limits and how functions behave as we approach a particular value of x. Now we're going to use what we know about limits to study an idea called continuity. And this is very important. The idea of continuity is very important in calculus. Continuity describes whether a function's graph is connected or whether it has breaks or holes or jumps or asymptotes. So the intuitive idea of continuity, which you may have heard before, is can I draw the entire graph without lifting up my pencil? If you can trace the entire graph without lifting your pencil from the page, then the function is continuous. That is the concept of continuity, but there's a lot more details that go into it, and we'll get into that in just a little bit. There are a lot of functions such as lines, polynomial functions that have graphs that are continuous over all the real numbers. And that means their graphs have no breaks or holes, interruptions. The whole thing is connected from beginning to end. And when I say beginning to end, I don't mean that the function has a beginning point or a starting point, because if it's continuous on the real numbers, then it goes on without bound in either direction. What I mean by the start and the end point is where you would put your pencil down and lift your pencil up, where you draw your arrows. So if there's a point where you have to pick up your pencil to draw the function, and there's a break in the graph of some kind, that's called a point of discontinuity. So to start, I want you to focus on what it means for a function to be continuous at a single point. So if I randomly pick a point on the graph, what does it mean to be continuous at that specific point? So in other words, if we zoom in on the graph near that point, the function should behave smoothly and the graph should all remain connected. So before we look at the formal definition of continuity, we're going to take a look at some examples where functions fail to be continuous. And by looking at these examples, we'll be able to identify the conditions that have to be true. Those would be the details that go into the definition. What are the conditions that need to be met? All right, so looking at this graph, we have a hole in the graph. Notice that the hole is on the graph at x is equal to a. Now, if I wanted to trace this graph left to right, I would have to pick up my pencil when I get to x equals a on the graph because there's a hole there, and then I would have to put it back down to skip over the hole and to keep going. So even though it's approaching this value, I'll call this value L. Even though it's approaching that value, the value of the function at x equals a does not exist. So this is just one of the conditions we need to meet in order for a function to be continuous. It's one of those official conditions in the definition. So the first condition is if we're looking to see if a point is continuous, that point on the graph needs to be defined. That's condition number one. Let's look at the next condition. So here's an example where the value of the function f of a is defined. It's defined right here. If I call this right here L1 and L2, I have a value at a. When x is a, y is L1. That's not an arrow. That's actually parentheses that I messed up. Let me fix that. Okay, so I have a point for y at x equals to a, so it's defined. But I still cannot draw the graph from left to right without picking up my pencil. There's still a break in the graph at x equals a. What causes that break in the graph is that there's a jump. And what causes the jump is that the limit from the left is L1, but coming from the right, the limit is L2. Let's take a look at that. So as I'm coming in from the right, I'm approaching the y value L2. If I'm coming in from the left, I'm approaching the value L1. So this is the second condition that needs to be met. The limit from the right has to be equal to the limit from the left. The first condition was that the value of the function needs to be defined at f of a. Now we have a second condition that we have to meet. The limit from the left has to be the same as the limit from the right, so they meet up and there isn't a jump. Let's look at the next condition. So now we have a function that's defined at f of a. So let me call this L1. Let's call this L2. So we have a value of the function at f of a. We're calling it L2. So we have the point A, L2. So that's defined. Now if I look at this, coming in from the left and coming in from the right, if I trace this function, the limit from the left and the limit from the right both equal L1. So the second condition is now met. But what makes this now discontinuous is that the value of the function is not equal to the two-sided limit. So that's the third condition that we need to meet. So the first condition is the value of the function has to be defined. The second condition is that both limits coming in from the left and the right have to be the same, so we don't have a jump. And now we have the third condition, so that the value of the function has to be equal to the limit. So now we have the official definition of continuity. In order for a function to be continuous at a specific point x equals a, we have that f of a is defined, the limit exists so that the right hand and the left hand limit are the same, and then the third condition is that f of a is equal to the limit coming in from both sides. So as we've just seen from the previous examples, not all discontinuities look the same. So mathematicians classify discontinuities into three major categories. And we have the first category would be considered a removable discontinuity. We have a jump discontinuity, and we have an infinite discontinuity. And we're going to take a look at each one of these individually. So let's take a look at graph A. We're going to start with a removable discontinuity first. Now, a removable discontinuity occurs when there's a hole in the graph. The function gets really close to the same y value coming in from either direction, so the limit exists. But the function itself either has no value at that value of x is equal to a, or the value of the function is assigned something different than what the limit is. So think of the graph with just one missing piece and the problem only at a single point. If we could remove that discontinuity simply by plugging the hole with the correct point, that's when you want to think of that discontinuity as a removable discontinuity. Next, we have a jump discontinuity. A jump discontinuity, we're looking at graph B now in the center. It jumps from one value to another. So as we approach the x value from the left, the y value or the value of the function is different than if we approach from the right. So that would cause a jump in the graph. And then finally, we have the infinite discontinuity. And an infinite discontinuity occurs when the function increases or decreases without bound as it approaches a certain value of x. On the graph, this happens at a vertical asymptote. So instead of approaching a finite value, a specific value, the function heads towards positive or negative infinity. So as you start studying these three types of discontinuities, the key difference is that a removable discontinuity has a hole, a jump discontinuity has a break where the two sides don't meet, and an infinite discontinuity occurs when you have a vertical asymptote. Now keep in mind that these are three of the most common types of discontinuities you'll encounter in calculus, but they're not the only possibilities. Some functions have more complicated behaviors that don't fit neatly into one of these three categories. But for now, just recognize that these are three basic kinds of discontinuity.